All right, please allow me to introduce Dr. Bill Philpott. Dr. Philpott is a professor in the Civil and Environmental Engineering Department at Cornell University. While his field is remote sensing, his perspective is in changing and understanding the interaction of light with the Earth's surface, such as water, vegetation, and soil. He began as a graduate student in marine studies at the University of Delaware studying coastal oceanography, but has come to consider other water and land applications including agriculture, forestry, geology, and others. Bill's current interest is in characterizing wet soils. Bill will be presenting on spectral reflectance of wet soils, implications for modeling.
Thank you. And oh, wow. That's great. Can you all hear me? Or should I wear a microphone?
You're good.
I'm good?
Okay, just look at the front.
Something that occurred to me is when I was a graduate student in oceanography, I wanted to do field spectroscopy and called around to companies, and this is in the 70s, to see if I could find one. And was met generally with about 5 seconds of absolute silence because they did not exist. I really do appreciate these instruments, just as a note. Okay, yeah, I'm interested in how wet soils affect spectral reflectance. And I've been using this slide for a long time. It's the best one I've found, and it's right north of Cornell. It's in Ithaca. But you can see the drainage patterns in the soil. Because I've been saying because they're wet. And, I also need to introduce Cha Tian, who is sitting back there. All of the data that I'm going to show are data that she has collected and were used for her thesis, and she's continuing on, so I'm usurping much of her work. But at her thesis defense, one of the faculty members said, that isn't necessarily wet, because water brings different materials as it drains, and it deposits them along the way. So that could be dry soil with different materials. I say it's wet. Okay. And spectrally, if I could look at that spectrally, I could prove that, but I have to make that point now. Okay, but wet soil darkens, water darkens the soil. So what I'm interested in is what are those spectral changes and how does that tell you more about the soil? Not just can you pull out the wetness, but can you tell something about the soil itself? And just want to understand what's going on there. Okay, whoa. All right. I'm going to repeat some slides that I showed at an ASD symposium 6 years ago. Is it me?
Reseat the connector.
Okay. This could be an exciting presentation, I guess, in the ways I don't intend. If I don't touch it, the spectra that you're flickering at you is data from Lobel and Asner of 2002. And they collected periodically, as soil dried, they collected spectra just to come up with a model and some description about what was going on. And maybe there's another connector here that would work. Is this? Try that one. They just don't know. Pardon? When do you do that? Okay. Sorry about that. Looks stable? Okay. Some things to point out. This is, the black line is the saturated soil. So it's, the blue line up here is air dry. I'm sorry, the gray line is air dry, the blue line is oven dried soil. Okay. So first of all, soil gets darker as you get it wet. Now, this is the visible. This grayed out area is the visible. So this is what we're seeing. And yeah, it gets darker. Eventually, before it gets too wet, it just gets stabilizes in color. That changes. You get much more range when you get out to the infrared, and a tremendous range when you get to the shortwave infrared in the change in color. Now, I was coming at this from an understanding of water, and when I looked at that, I thought, that's just the water absorption spectrum. That's all we're seeing. I can model this very easily. No sweat. Easy. And I did. And what I got was a set of models. These are the 4 data sets that Lovell and Asner collected. And my model is the dotted lines that overlay that. Okay, not bad, but it was honestly, it was a terrible model. It's not good physical ideas. It was just throwing something together saying I can match those curves. And I'll point out where I can't. In here, in particular, it could not match that consistently. In this particular case, it could. Here, not so much. Here, it's particularly bad, and it missed. I was missing some very important physical properties of the soil. So that model was crude. It got my interest, and I finally found out how complicated soils were and moved on to looking at this. Okay. So this is my favorite slide. Just because it fits doesn't mean you can believe it. Okay. All right. These are the 3 soils that Chad measured. We chose those because they are so different. We have the quartz sand, which is very large, coarse sand, the masonry sand, which is relatively fine sand and darker, multiple materials, and then Ithaca soil, which is sort of typical soil of this region, very, a clay loam, silty loam soil. It's some very small particles, very different colors. So we've got a range of things going on with this. This is our setup. This is our goniometer. This device here, homemade, very much like, well, homemade. It's like chips in that it's homemade. It's not like chips in that it's much simpler. It's just a one-dimensional piece. But the thing is, we were using an 8-degree field of view, looking at the soil sitting on a scale. We measure the amount of water that's remaining in the sample by weight. So it's filled, it's saturated, and we watch the soil dry. So that's what we do. We watch soil dry. The basic idea is is fairly large sample holder, field of view of the 8 degree field of view detector. We're now using a 3 degree field of view detector to get in there. Also wanted to have a microscope to watch the thing as it's drying. This is kind of fun. movie of soil drying, right? That would be my next YouTube video. In order to put the water in and not disturb the surface, you have a little port on the side that inserts the water at the base so the water can infiltrate up. The idea is to minimize the amount of air space that holds out in the pores. If you pour in the top, you could get potentially some remaining air spaces in the pores. Hopefully, if you put it in at the bottom, it's absorbed up, it percolates up, and fills all the spaces and becomes as saturated as possible. Back to the water absorption spectra, it's showing this in a little bit different form. I want to point out that there is a 6 order of magnitude difference in the range of the absorption coefficient from the visible, from the blue range, up to the shortwave infrared. That's a huge range. Things are going to be looking very different depending on when you're looking, which range you're looking at and what characteristics you're checking. So, and I want to point that out and sort of draw some implications from that. Okay, these are the spectra, or selected spectra that Cha made. And this is the quartz sand up here, the masonry sand here, and the Ithaca soil here. Wet to dry. Notice that the quartz sand starts off slowly, doesn't change much for a while, and this is a constant. Let me describe something here. The evaporation rate is constant. All the water loss is through evaporation. We have a sealed sample holder. All the water loss is from evaporation. It's drawing up the water from the volume, keeping a fairly uniform water surface, and constant evaporation rate up to this point. Constant evaporation here, up to that point. Constant evaporation here, up to this point. All of this change it's not a uniform change with the rate of loss of water, which was interesting right away. But look at the differences between the soils. This goes up, stops, basically, looks the same for a while, and then slowly increased, and then a huge jump in a very short period of time. These are 1-hour intervals. With the masonry sand, it basically does not change initially, gradually changes, and then huge leap. With the Ithaca soil, the very small particles, first of all, it's saturated and doesn't change. It just hangs out. Then the water content begins to change. It changes almost steadily until here, and then a leap. Okay, so something's very different. Primarily, it's the particle size distribution. It's the pore spacing that's different. It's changing the way the water is held in the soil. And that's changing the reflectance properties. Okay. Let me go back. Okay. It won't go back, so. Well, it will go back slowly. Chow looked at this and thought, what's the most sensitive? Right here. Here. At the water absorption bands. That should be the most sensitive to the water content. Why don't we look at that? And the idea was that, well, the more water there is, the deeper this depth of this feature should be. So as the water content increases, that should increase. That height should increase. And this is sort of the model that we were thinking of. This is at the 970 and 1160 nanometer water absorption bands. And yeah, that's what you're getting. We only saw this, though, with the quartz sand. So this nice linear change, or nearly linear change, with reflectance to water content was there. What we saw with the others, first of all, in the other sands, in the other soils, we didn't even see the water absorption band at 970 and 1160. It wasn't there. I'll explain that in a minute. We did see it at 1440 and 1930, but it was not a nice, simple relationship with the water content. and this was problematic, particularly here, where instead of the depth of the water absorption band increasing as the water content increased, it decreased. This is not good. This was not our idea. So the next piece was to model this, try to see if we could describe what was going on with this very little. If the other order, if the first model was a 0th order, this is maybe a half order model. It's just a little bit better. But the idea was gradients coming in, a little bit reflected off the surface, air-water surface, some absorption through the water, reflected off the soil-water interface, back up through the water, some reflected, some lost right here at the water-air interface, and measure that. That means that we get the reflectance, it's just the downwelling irradiance and the upwelling irradiance over the downwelling irradiance, and we get then one reflection from the water-soil interface, two reflections from the water-air interface, and the attenuation through the water. That's it. Very simple. Just a layer of water over a uniform soil surface. And what we got was the curves down here. And to my surprise, they look an awful lot like the curves that we got for the soil. We have this nearly linear transformation for the 970 and 1160 bands, this slow curve for the 1440 band, and the peak and quick drop off for the 1930 band. So it could explain a little bit of what's going on. And you see, that's the quartz sand. Okay, it's not a great model. I'm not suggesting that you use this really absolutely apply it, but it gives us the right shapes. It gives us the right idea. Oh, and then if we take the derivative of this difference with respect to the thickness of the water layer, you can solve for the thickness of the water layer at that point. And that tells me that roughly it's going to be at about 100 microns. When you get a water layer that thickness of 100 microns, then that's going to be a peak. Well, probably what's happening is that the bulk of the water has sorry, I'm having a little trouble learning this. The bulk of the water has gone right in here. The water is absorbed onto the particle surfaces. It's not in the pores anymore, and that's what we're seeing, and that's where we're getting this very thin layer of water. One other piece on this is that this is the evaporation rate. So computing the evaporation rate and just monitoring it over time is virtually constant for all three soils for most of the drying period. At the end of the drying period, it takes a dive. Here, there is pore water, and it's feeding. Let me describe what's probably going on. It's saturated to begin with. The soil is absolutely saturated at the beginning. Only losses from evaporation. If some water evaporates, it draws water up. The capillary forces are greater than the gravitational forces in the water and the soil surface. So it just pulls water up. Eventually, some air pockets form in the soil. And it's not uniform. An air pocket will appear in one spot, an air pocket will appear in another spot, usually in the larger pore spaces. So they'll show up there first. Eventually, all the pore water, the available pore water will be gone. There'll just be meniscus in between the soils and water absorbed onto the soils. At the end, that water eventually comes out, and all that's left is the absorbed water, and then that goes. What we're seeing here, right here, is we've gotten to the point where there's only absorbed water, and that's dropping off. So we're getting a change in the evaporation rate. It's decreasing at that point. Up until that point, there's always some liquid water to draw from, and then you lose it. Well, entirely fortuitously, this drop-off occurs at the same time as that. We're looking at different things. We're looking at reflectance and we're looking at evaporation rate, and they happen to coincide when the water adsorbed to the particles is disappearing and you're starting to see some particle left over. It happens with all of the soils, no matter what, even though the timing is very different. With the volume water content or with the actual time, we're seeing the same sort of thing going on. And it's here is where it happens. Here is where it happens, and in here, between the brown and the, it's a slower change here, but it's the same thing going on. Okay. So we've got some physical relationship between the change in reflectance and what's going on with the water in the soils. Let's see. I think that's okay. So I had a few implications. First, water absorption in the shortwave infrared. Water absorption controls the change in reflectance. Let me go back one slide and point out something. I can't see it well here. See this feature? That's a soil absorption feature. That appears when the soil is dry. Notice that it disappears as we go down, and it doesn't take much water to wipe that out. The water absorption is wiping out the soil characteristic features. They're gone. That even happens here. Let's see. Yeah, here. You can see it better in the masonry sand. That's the soil absorption feature. It's gone. So water's controlling the color change in even on both the magnitude and in the subtleties. It's controlling the reflectance characteristics. Soil spectral features are masked by the water absorption, and water masks the soil. The water optical path is a useful metric. So and that's going to be a spectrally changing thing. How far is the light getting through the water before it's pretty much gone? I can go into that more if anybody's interested later. But okay. Water absorption is strongly wavelength dependent, so we're going to have different types of effects in different ranges. Notice we really couldn't see the SWIR1 absorption bands, if you will, the shorter wavelength absorption bands, in anything but the quartz sand, because the water optical path was only long enough in the quartz sand in order to be able to see those absorption features. In the far longer wavelengths, we could see the same. We could see the absorption bands in all of the soils. Then water optical path is going to be related. It's going to be related to the size and distribution of the particles and the size and distribution of the pore spaces. The rate of change, the characteristic bands that are available and the way they change are going to be related to the pore spaces and the particle sizes. The disposition of the water. Where is it? Is it liquid water in the pores? Is it absorbed on the surfaces? Is it in menisci in between the particles? So those are going to be controlling that, which also suggests that this should change with angle. We have a goniometer. We haven't used it we haven't made all the measurements at angles yet, but we expect significant changes in the spectral reflectance as we change the viewing angle and as the water content changes. Okay, I've got to move a little more quickly here. Go back to this, the water absorption. Okay, here, the water optical, the attenuation length, they've got an absorption of 0.1 per centimeter. So an attenuation length over a millimeter or so. In here, there's virtually no attenuation by water over these lengths. We've got millimeters at most of water. It's not going to be absorbing. It's not going to be scattering. It's got to affect the reflection in some other way. And just to prove it, in the visible, even in the red, this is about a foot-deep tank, and we can see every possible color within our visual range, from blue to red. Water's not terribly removing much of the light. At 10 meters, if you're a diver and you go 10 meters, yeah, red's gone. But at a few millimeters, no, it's there. So is the shortwave. So is the very near infrared. It's there. Water's not absorbing. It's not long enough path length to scatter much. It can only change the color of the water by changing the relative index of refraction. So the light comes in, it's more likely to be scattered forward. It's more likely going to change the interaction there. What's happening is that it's enhancing the absorption by the soil. Or that's my hypothesis, at least. So my hypothesis here, absorption and scattering by water, pure water, is negligible at these distances. The darkening results from soil absorption and improved soil absorption because there's more multiple scattering, light's getting deeper into the soil, more opportunity for absorption, more light's absorbed. But it's absorbed by the soil. And then, since the particle diameter is much less than the wavelength, and the wavelength is, much less than 1 micron, and the wavelength much greater than 1 micron, particle sizes are much greater than 1 micron. The wavelength is much less than the micron. I'm going to assume that the scattering phase function is constant over this range, over this wavelength independent. I don't know what it is, but assume it's constant. So the veneer color of the soil will not change as the reflectance decreases. Okay, so no color change, just amplitude change. And now, probably everybody here knows the vegetation index, the normalized difference vegetation index. But this is in Maryland. This is Delaware Peninsula. This is hyperspectral imagery. This is just 675, the red versus the infrared band at 877. The scatter plot has been converted to reflectance, so the NDVI should work. Along the diagonal would be an NDVI of 0, and an NDVI up to 1 up here, and here's a soil line. And if I block that out, oh, I got this. Okay, I've got 2 different types of soil. I've got outlined in green here and outlined in blue there. I've got the bright soil and the darker soil. Let me go back so you can see. I have 2 types of soil basically here, outlined in the scatter plot. And I can outline them there very neatly by just, my hypothesis then is that the main difference here is from dry to wet, from dry to wet, and that will obtain in every spectral band through the visible, through the near infrared, up to about 900 nanometers. As long as the water absorption is low enough. So that line, it doesn't. Maybe it's not just dry to wet. Maybe it's a little different material in there, but that's the idea. Okay. If that hypothesis is true, then if I took the principal components analysis of those spectra of the soils from wet to dry, the first principal component should have 99% of the variance. And most of the variance that's left over, explained by the remaining principal components, should be pretty much random. Okay. Well, this is using Chow's data for the quartz sand. It's pretty linear, as predicted. It falls along the line, the radial line to the 0, point, so there's no color change, at least in these 2 bands. So far, so good. Go to the masonry sand. It's not bad, but point out that there's a little bit of a curve here. It gets a little brighter in the infrared, a little dark, and then darkens down here. It's also a peculiar increase. It gets darker, 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 and then brightens. Anybody have any ideas what that is? I'll show you in a minute. All right. And then the Ithaca soil is more shifted. It's more infrared than red than the other. So the color, the basic color is a little bit different, but it follows this there. follows that basic line, also has a return. You can see it strongly there. This is supersaturated soil. It's not only is the water in the pore spaces, it's actually on the surface, making a continuous water surface. You're seeing specular reflection from the surface. Here. So you can see dry, drying, wet, and saturated. This saturated is actually brighter than that, just because of the specular reflection on the surface. So I really shouldn't, this is oversaturated, a little bit too much water. It's almost a continuous water surface, and the orientation of the surface is directing water into the detector. That's why you get that last little bit of increase. Okay, but basically the color has not changed. It's brighter to darker, but the color has not changed. If I look at the principal components of the spectra, this is the first principal component versus the second principal component, but no scaling. This is scaled to stretch the second principal component. This is virtually linear. So there's no appreciable change in color as you're adding the water. These, by the way, are the eigenvectors. So this shape, the blue, is the first principal component, the first eigenvector. It's basically the color spectrum of the soil in this range. The second eigenvector, the red, is a contrast between the infrared, which is positive numbers, and the red and the visible, which are negative numbers. Third principal component kind of contrasts the middle range to the end ranges, but it's noisy, and the 99.7% of the variance for the first eigenvector, the first principal component, less than 3% of the variance in the second principal component, and a marginal amount in the third principal component. We've got 500 other principal components with less. Okay. This, by the way, is the dry to wet. Okay, this is not noise. There's something organized going on there. I don't know what that is, and if anybody has any thoughts, please let me know. I don't understand why that's not just random noise. The next, if I go to the masonry sand, again, I have 99.8% of the variance explained by the first principal component, less than 2%, 0.2% explained by the second principal component, and some really trivial amount in the third principal component. Again, the blue line is the first eigenvector, and that's essentially the spectrum, the reflectance spectrum of the material. Again, there's a contrast between the visible and the infrared. The sign has changed, negative to positive, but it's basically just a contrast. And the third principal component, I'm going to pretend is not there because it explains so little data. But this, now, the second principal component, there's structure there. Something's going on. Something's changed right there. I don't know what that is. So but there's something happening with that, the structure of the soil that's different. This is almost two linear lengths. This one's a continuous curve. I have no idea what that difference is, what could cause it. Last one, the Ithaca soil, again, 99.9% of the variance by the first principal component, less than 2% for the second, and something, again, very trivial for the third. And the second principal component, it's very small variance, but something's going on. Okay, my conclusions. I think my hypotheses were basically right. Absorption and scattering of pure water is negligible. It's really not affecting it affecting the spectrally directly. It darkens the soil, darkening as a result of soil absorption, and that's explained by the first principal component being 99.9% of the variance. And the veneer color does not change as the reflectance decreases. doesn't really change subtly. There is coherent color information, though, in the second PC, so there is some color change. Represents a contrast between the near-infrared and the visible. So it's got to be either subtle water absorption effects or some wavelength dependent of the scattering phase function. Or maybe somebody else has another suggestion. No hands going up.
Yeah.
You done?
I'll wait till the end if you want.
Okay, just I'm basically there. This is my last slide. Oh, and yeah, that's the last slide I intended to show. All right. Then I'll be happy to take questions. Yes.
Oh, no, go ahead. You're fine.
One of the amount of scattering you get at each, you get scattered anytime there's an index refraction change. And when you put water in there, you replace the air with water.
Right.
And the water doesn't have a constant index of refraction across the wavelength range. But if you look at the wavelength dependence of index of refraction of water, it actually has the same shape, very similar to your second PC. So I'm wondering if that is
you might have something there. Right. That would be interesting. Wow. Okay.
Because so the amount of scattering you get off those grain water boundaries is going to have a wavelength dependence because the index of refraction of water changes.
You know,
from 400
you're absolutely right. I've been thinking of the index of refraction of water being virtually constant.
No.
But neither that or the soil is constant.
Right.
So
well, and
the
every mineral
combination-
grain is going to have its own little index of refraction function, and so it's the bigger the contrast, the more scattering you get. So the interaction of the index of refraction function of the water and the grains themselves will.
Nice. Thank you. Okay. Do we have time for one more? Just
Yeah, actually, two points. Some of these subtle water absorption effects that you were hitting on across all the different materials or all the different samples that you had could be explained by the clay content or the fines content. Did you look at that?
for the Ithaca soil, that's true. For the others, for the quartz and for the masonry sand, there was very little clay.
Okay.
There was very little organic material.
Yeah, and then the other thing is, my background is more from the soil mechanics side of things. So seeing sort of the measurements that you took over time, I think would be very interesting to look at from a water content or percent saturation point of view, as opposed to, because you're drying in a heterogeneous manner. You saw on the surface that one area was dry and one was not, and you're sampling that. But I think it'd be very interesting to actually create more of a homogeneous sample out of for each one, and actually just have one value of the water content in each sample.
I may need to talk to you a little bit more about that. Okay. All right.
Dr. Philpott.